Hey, good day here, and welcome. Day number 16 and the last of our lectures. And so by the time you get this video, you would have already taken the exam, number 3. And so I'll remind you, but it'd probably be too late. Don't forget you have exam number 3 at 11 o'clock here. So I'm going to finish up this filming here, this last lecture, and then I'm going to go sit at my desk. And so again, if you have any troubles, shoot me off an email. And of course, by the time you get this, your test is already over. But let me say the same thing for the final exam. The final exam tomorrow, that's all we do on the last day. Day number 17 is the final exam. So at 11 o'clock, again, I'll be sitting right there in front of the computer, and so you have any trouble, shoot me off an email. You have any questions, shoot me off an email, and I'll respond within a few minutes, I'm sure. Depends on how many other students might have problems and questions at that same time, or maybe other things that from other people emails. But from 11 to 2 o'clock, that's your final exam tomorrow. And so remember that you have a little more time. And the test is a little longer. I'll say it again, the final exam is 36 multiple choice questions and 11, so only one more than the regular 10 free response ones. And of course your test today, you just got done with, had 20 multiple choice and 10 free response. And so I'll be grading those tonight. And so at least I hope to tonight. If not tonight, tomorrow. And so I'll get on finishing up the grades and all your other stuff. And I do want to say, don't forget that you do have some homeworks and labs that are due. See, the homeworks would be chapters 15, 16, 17, and 18, the same chapters you just took the test on. Those are actually due. Canvas won't close the window until Wednesday night at midnight. So if you haven't got those turned in, do that now and get those in. And then also the last set of labs. I can't remember which labs they were. I know the one that I sent you last night was number 12. And 11 and 10, that might be it since the last test. There wasn't as much time between test 2 and test 3. So you don't have much to turn in, but you have until Wednesday night. And I would just encourage you, even if it's not, Wednesday night yet, if you're done, turn it in. Get it out of your way here, because like I said, we're about to wrap up here. And so let me begin this last lecture, this last chapter that we're going to have time to cover. It's another shifting of gears, and it'll be just enough time to kind of introduce you to the world of electricity and magnetism. And like I've said many times before, the real thrust of this class was to make sure we covered chapters 1 through 8. We spent a disproportional amount of time on those because that's what you need next, going through 121, where many of you will be taking it this fall. And many others of you will take it next spring because you probably have a little more calculus and a little more math to do before you're ready to take it this spring. And that's what then hopefully will get you through 121. And then you'll go into 122 and 123. And this material that we're talking about today is the material that'll be in 122. And so having a little bit of background to it is kind of nice, but not essential. And so that's why I decided, hey, let's use our time wisely for the mechanics early on in the semester, and then we won't have to, and then we know we'll be ready for 121, and then we won't have to worry too much about the details of electricity and magnetism. So this next couple of chapters, although we're only going to get a chance here to do one chapter, chapter 20, is on electricity. And the best way to start this is to really go back to chapter 11. And chapter 11, if you recall, was the first chapter on the structure of matter. And we looked at what does an atom look like. And we had a long discussion. It was kind of a long chapter. I wouldn't call it a hard chapter, but definitely a long chapter, where we were looking at the fundamentals of the structure of matter. And I started with helium and tried to point out that if we talk about the structure of helium, then the other atoms look a lot like helium. Now, they are different, and so we talked about how they were alike and how they were different. And I want to focus for a moment on how they are alike. And one of the things that we said during that time is that on the outside, orbiting around a nucleus, are these things called electrons. And I used this idea and said these electrons carry with them a charge, a negative charge. And then I said, let's just make that comment and then come back to it in chapter 20. So here we are. We're coming back to it in chapter 20. And so there's another basic physical quantity, just like mass, where we don't really try to explain the mass. We just say objects have mass. And that's true for these electrons. Electrons have mass. We could talk about their number. In fact, I'll put it on the board here. Their number, their mass anyways, is 9.11 times 10 to the negative 31 kilograms. That's the mass of an electron. And we didn't really try to explain why it had a mass. That's a much deeper discussion than we're ready to go at this level. But we just said it does have that, and so that's a fundamental property. It's like time. We know that time keeps ticking forward, right? We know we go from 1 second to another second to another second. But what really is time? Why does it go forward? Why doesn't it go backwards? Why doesn't it stop? Can we make it go faster in a forward direction or slower in a forward direction? What is the flow of time? And so there's a lot of interesting questions about time, but we just take it, hey, there is time. And time flows forward. And it always flows at that same rate. That's at least at the level we've been talking about in this class. And so I'm going to say the same thing here, that objects have mass, but they also have a charge. And charge may be less fundamental to you. And so I want to begin by comparing it to the mass and just say it is a fundamental property. And if you let me just start there, that they have charge. Let's not try to ask more detail of where the charge comes from and what exactly is charge, just like we did with mass and time. But let's go forward in the other direction and say, okay, if they do have charge, what does that mean? What do you mean by having charge? What kind of interactions, what kind of things happen? And so that's where I want to begin here. And so I'm going to say that these electrons have a fundamental property. Besides having mass, they also have a charge. The same thing is true about the protons. The protons, if you recall back in chapter 11, carry with them this fundamental property called a charge. Now, it's a different charge than the electron. In fact, you might say it is exactly equal and opposite. That was discovered by Benjamin Franklin. And he said that there was only then two types. And so he ran a bunch of experiments very similar to what I'm going to do over here. And as he studied the result, he was able to conclude that all of these interesting physics phenomenon that is taking place was all based upon two different types of charges. Now, he didn't know as much as I'm explaining to you that the atom looked like this, that the atom had a nucleus, that the atom then in the nucleus had what he called the positive charge. He just knew there was positive charges somewhere in his sample. He also knew there were negative charges and somewhere in his sample. But he didn't really know that they were associated with the electron or the proton. And so we know more than Franklin, but we still know that there are only these two types, a positive and a negative. So of course, we will label things negative by putting a minus sign, and of course, things positive with a positive sign. Oh, that's probably why you noticed when I talked about these electrons, I put an E for the electron, but I also put a negative. That's kind of the universal symbol for the electron. The E, because it's an electron. All right, good. We'll come back. We lost power again here, and so we're back up and running. And I think when we lost power, I was just saying here that the whole discussion of chapter 11 and the structure of the matter was to show you that we have these two types, a plus and a minus. And I was saying how the electron, we use this little symbol for it. Actually, in the proton, too, we like to put a P with a plus sign. And so P for the proton, and then plus because it has a positive charge here. But Franklin ran a bunch of experiments, as I was saying, and I want to come over here to the table and show you a bunch of these experiments. But I want to put two things on the board that I hope I successfully demonstrate here, and that is like charges repel themselves. And the second thing is that unlike charges attract. And the phrasing of it sounds kind of weird because it doesn't say positive and negative, but here's what we mean by that. When we say like charges, and the reason we use that phrase like charges is we say if you had something that was positive and another one that is positive, that's what we mean by like charges. Or if you had something, and so I'll put or, something that was negative and something else that was negative. That's what we mean by like charges. And so I hope to demonstrate to you in a few moments here that if I put the two positives near each other, there will be what we're going to call an electrical force, not a gravitational force, an electrical force. And they will repel each other. And so we're kind of adding to our physics of what can happen in the world. And so instead of having forces involving gravities and pushes and pulls that we've been doing all semester long, which those are good. And when I say pushes and pulls, I mean like with a rope or a cable or a hand. We've been talking about those, but we really haven't really talked about down on the microscopic level, down where your hand, where the electrons or the protons push on each other. And so that's what I want to illustrate. And so we've got some good examples. In fact, before our lecture is over, I think this chapter, since it's the end, and also because it's new stuff and different stuff, I think maybe the best way to do this is I'm going to actually then turn to your homework. And I marked 1, 2, 3, 4, 5, 6, 7, 8 different homework problems that I'd like to work through with you, because I know in the past they've been a little challenging for students, but also I just think it's a better way of teaching it, especially near the very end and the wrap up of this semester here. Now, coming back to unlike charges, this would be, again, kind of a universal phrase of saying, what if you had the first one positive and the second one negative, or the other way around, the first one negative or the second one positive? Doesn't really matter, but they are going to end up attracting each other. And again, hopefully you will see that. Now, there's a third principle. I was going to hold off on putting it on the board, but once I get started on here, I'll probably forget to write it here. So let me go ahead and just put that I will also demonstrate another fundamental property here, and that is that we have conservation of charge. And what I mean by that is the total charge is conserved. In other words, the total doesn't change. In fact, now that you kind of see these principles, even though I haven't demonstrated them yet, maybe now it makes more sense. While back in chapter 11, I was saying things like this, that when we figure out how many protons it has, and so taking this big chart and looking at helium where it has atomic number 2, and we said, okay, that tells us how many protons it has. And of course, the 4 tells us how many nucleons it has, so that would mean that it has 2 more neutrons. I said, then how many electrons does it have? And I made this comment. That it would prefer to have an equal number of electrons. It didn't have to. We called those ions, but we said if in a normal situation, it would want to have the same amount. And now we begin to see why I make that statement. I make that statement right here because unlike charges attract. So if you didn't have any electrons here, then you would just have the 2 protons, and the 2 protons would then say it's positive, and so it would want to grab the electrons, and so it wants them. And it only wants 2, because if it had 3, now, again, I would say it has more negatives, and the negatives end up dominating and repel more than the attraction between them. And so it wants to have an equal balance. We're going to use the phrase neutral. And that's an important phrase. Neutral does not mean 0 charge. Neutral means an equal number of positives and negatives. And so understanding this principle, which again I need to show you this principle, so maybe I just better get over there to the table, you'll begin to see why we made that earlier statement that the matter wants to have an equal number of protons and an equal number of neutrons. Well, let me come over here and see if I can demonstrate here. And I'll take some more exotic material than Franklin had to work with. Let me move this forward. This little strip that is a little blue in color, but mostly clear, compared to the other one, which is definitely more clear, is vinyl. So this one's vinyl, and the clear one is acetate. And so these materials work better than Franklin had, so I'm going to use them. But as long as I'm mentioning it, here's what Franklin had. He had natural rubber and glass. And so he would hang this natural rubber one, and so this would be like my vinyl. And then the glass would be like the acetate here. And so these have that same overall properties. But today's materials, we can see it better, and so that's why I want to do it, because it's still hard to do, especially on a humid and wet day like our June gloom. So I'll keep my fingers crossed here to make sure our experiment comes out well here. But watch this for a moment. I have another piece of vinyl, and so let's just focus on this vinyl and this vinyl. So I got 2 pieces of vinyl, and the important thing is to point out that they are the same material. Because if I take a piece of vinyl and I rub it, and so I just grab the piece of paper, it could be any material. It does work well with paper, so that's why I grab the paper, but I rub it. Now, let me come over here and show you the structure of matter here. The structure of matter, remember, is a nucleus with electrons on the outside. So if I take a piece of paper and a piece of vinyl, but again, it could be any materials, but this works really well. Paper and vinyl, and I put them together and I rub them together. What parts of the atoms actually bump into each other? And I tell you, I'm taking my right hand and I'm squeezing hard. And so I'm rubbing back and forth and I'm squeezing hard. And so as I squeeze hard, what actually bumps? This would be like saying, if you put 2 cars together and you rub them, well, what parts of the car bump and get damaged, if you will? Well, you're going to say it's the bumpers, right? It's the outside of the car. It's not the inside of the car. I mean, the passenger seat or the driver's seat doesn't get damaged when you take 2 cars and put them together and rub them. It's the stuff on the outside that's touching. And that's exactly my point here, is that if I put another atom next to this one, so I put paper atoms next to vinyl atoms. Yeah, they're carbon, okay. But if I put them next to each other and I rub, then these electrons that are in the vinyl are then bumping and rubbing the electrons that are in the paper. And essentially I tear them off. And so again, imagine 2 cars, you're rubbing them, and if you rub them hard, you're going to tear off their bumpers. You don't tear out the seats, you tear out the bumper. And here's the neat thing about it. Remember, they want to attract back. Now, I haven't shown you that yet, but I'm going to. But if you take this on its face value, those electrons want to go back. But what if, like 2 cars, where you rub them together and you tear off the bumpers, and let's just say the bumpers are made out of steel, and let's say the cars are magnetized, but one is more magnetized than the other. You see how it might be possible that the 2 bumpers now go to 1 car? In other words, the one car that is more magnetized gets not only the original bumper, but it gets the bumper from the other car. So one car has two bumpers and the other car has no bumper. And that's exactly what's going to happen here. When I take vinyl and I rub it, I am tearing electrons off of the vinyl and off of the paper, and they're kind of freely floating around. But they want to come back, and they want to come back more to the vinyl. That's why I'm using vinyl. Vinyl is what we would call in chemistry very electronegative. It loves electrons. It loves it way more than paper. And so when I rub this, here's what I'm claiming. I'm claiming that I'm essentially taking electrons away from the paper and onto the vinyl. And so let me pause right here. That description that I just said is really using the principle of conservation of charge. You see, here's what I'm trying to do. I am trying to make this vinyl piece charged. I am trying to have it be more negative or maybe more positive. At this point, I don't really care. I just don't want it to have an equal number of positives and negatives. When I first picked it up, it looked like this. It had a bunch of protons and an equally bunch of electrons. And I would say when I picked it up, it is neutral. In fact, this one over here, I would say this one is still neutral. The one that's hanging is neutral. I haven't rubbed it. And it's been sitting out here all night. I set it up last night. It's been sitting here. And if it wasn't, electrons would have come and gone. And it may take a while. And so this one too may take a while. But right now, it is negatively charged, where this one is neutral. And so this principle of conservation of charge is real important in understanding that, hey, we don't just make these electrons out of empty space. You don't rub things together and create new electrons. When I say conservation of charge, the total charge is conserved, what I'm saying then is this one has extra electrons on it, so I'm going to call it negative, and this one here is now lacking electrons. Now, if it lacks electrons, that means it is positive, because there's more positives than there are negatives. And so keep in mind here that I'm trying to demonstrate that when we work with electricity, the stuff that moves around is the stuff on the outside. Again, like cars. When you rub them together, the stuff that moves around is a bumper. But just because you can only move bumpers, or in this case, just because I can only move electrons, doesn't mean I can't make it something positive. I can make it positive because I take electrons off of it. So this piece of paper right now is positive. This is now negative. Now, here's what I want to show you then. Maybe I will, where can I put this? Well, I'll hold it with my teeth so I don't lose it. But I'm going to do the same thing with this piece of vinyl. And so, as I rub it, and again, conservation of charge, electrons are being transferred from the paper to the vinyl. And I'm hoping then you will be able to see that these two pieces of vinyl now repel each other. I can even chase it around in a circle. And so this is my experiment of showing you that if I take, and see, I guess it would be right here, two negatives and bring them near each other, they're like charges, they are then repelling each other. Well, let's watch it again. This is why I did the other material, the acetate. As I said, the acetate is equivalent to what Benjamin Franklin did. And Benjamin Franklin used glass. This one's even harder to work, so let me rub this one extra hard. But it's the same type of logic. When I rub these two together, the paper and the acetate, the things that are rubbing are the outside. And so the electrons are being scraped free, again, like two bumpers on a car. Now those bumpers are free. But one material is usually more attractive than the other. That's why you've got to have different materials. And so my example was the car. If one car is more magnetized and the bumpers are made out of steel, it'll be attracted a little bit more towards one car versus the other. And so as I rub these two, this time, the paper is more attractive to the electrons than the acetate. In fact, if kind of looking at the three materials I have, the vinyl is the most attractive to the electrons, and the acetate is the least, and paper is kind of right in the middle of those two. And so I have found over the years that this tends to be a nice blend where I can actually then use the piece of paper then for rubbing both materials, but yet have one material, this one, which is going to be positive, because when I scrape this, the electrons free off and then they go to the paper. In fact, they want to extra go to the paper because remember the paper was already positive when I took them off of here. So the paper is actually very happy with me now because I'm tearing the electrons off of the acetate and bringing it over to the paper. So let me do two acetate. So this is my first acetate piece, and I've rubbed it pretty good. Let me just kind of hold it in my mouth and come over here to this hanging acetate piece and rub it. And I rub it hard. And I hope that's enough. This is kind of a tougher one to see. Ah, good. Seems to be working well. But you can see then that this acetate and the two acetates repel. And so I would say I'm doing this right here. I am showing you, hey, I've got two positives and they repel each other. And so that's my phrase here. Like charges repel. Whether they're both positive or both negative, they repel. Now, the other half of this down here is the unlikes attract. So let me take this piece of acetate, which is positive in my hand, and let me bring it to the vinyl that is now hanging here. And I think I will, just rub it. Just in case some of the electrons have left, because again, they will slowly leave. They don't like to be there. But now I should have a positive here and a negative here, and let's see what happens when I bring them together. Ah, yeah. See? I'll get behind it and slow it down, and it's attracting. And I can even make it chase it. And so this positive is then attracted to that negative. And so I guess I would say I'm showing you this. Here's the positive, here's the acetate, here's the negative, here's the vinyl. And I could do the other way around, but I think once you see that one, this one's pretty obvious. But I'll do this one. And so let me come back over here and grab a negative in my hand. And so this is the vinyl, the blue one here. So I'll make sure it's good and negative in case it lost something when I set it down and touched the table. And so this is going to be negative. And of course this acetate, I'm going to take a risk here and see if it's still positive. And if I bring it near it, yeah, sure enough, it attracts it. Put it behind it. I should slow it down and make it come back. And I make it chase it. Whoa. Maybe put it behind it, slow it down, slow it down, slow it down, and chase it. And so, sure enough, they attract. And so the fundamental physics of this chapter and the fundamental idea of electricity is really based on that principle. That, I'll say it again, unlike charges repel each other, like charges repel each other, unlike charges attract one another, and to make things positive and negative, you're really just shifting it around. You don't ever make any electrons, you don't lose any electrons, you just shift them around. And notice again, I'm saying you're shifting around the electrons. You're not shifting around the protons. The protons, remember, are in the nucleus of the atom. And so take that piece of vinyl, which is made out of carbon. And carbon, as I look up here, are atoms that have, let's see, atomic number 6. So they've got 6 protons in them. I am not moving the carbon atoms from one to another. I'm not moving positives around. I am only moving the negatives. And that's the big picture. And everything else in this chapter and the chapters that follow, which we won't have time to do this semester, but as we get into Physics 122 and as we do more of that, you'll hear me say it over and over again that keep in mind the fundamental idea. This is the fundamental idea. And if you keep these 3 things in your mind, most of the things we're about to explain and talk about, they just fall into place. They're what I call deductive reasoning. You know, physics is about knowing how to use a few very powerful, fundamental concepts to explain a universe of phenomena. And so you've seen me and heard me mention that a few times, and that's this whole idea. Now, here's a fun one that threw the early scientists, including Franklin, for a little bit of a loop for a while until I kind of figured out what was going on. What if I did something like this? What if I took something that was negative and I brought it near something that was neutral, uncharged? See, because what we've seen so far and what we've mentioned so far is that we would have an interaction if they are charged, if both of them are charged. And this is saying, what if we have a negative and a neutral? And of course, I can set that up here. Here's going to be my neutral object. Here's a little hanging light piece of cork. Purposely, it's light, so I can see if there's any kind of push or pull. But also, let me maybe get this a little further away. But also, this is set up so that you can see if the push or the pull is one way or the other, and whether or not it will affect this positive or negative. Let me grab my negative. Here's the negative. And I did something with that piece of paper, but I might as well grab another one here. I think I've butchered that piece of paper pretty good, so maybe it's time to butcher another one. And so I'll fold it and rub. And maybe, well, I was going to say maybe before I rub, I should have brought it near it to kind of show you it's neutral. Maybe I'll demonstrate an important technique. If it wasn't neutral, let's say it had a couple of extra 100 electrons on it. If I do this and touch it, remember, they're negative. They don't like each other, right? They're like charges, they repel. They will then flow off the surface of that piece of cork and then onto me. And they want to go onto me because they can spread out further. The general rule is we like to say, if you take a big object, so me being the big object, and you touch a small object, because the electrons want to get away, and getting away from each other, they can get further apart on a big object, they will then do that. They will then leave and go to a big object. So I'm going to touch it just to double check that it's neutral, but it also gives me a chance to say, we often call this grounding an object or neutralizing an object. I'm not sure grounding would be the appropriate word. The best way of grounding is you touch the ground, but we say that because of all the objects around, what is the biggest object? And it's not me, it's the ground. In fact, if I wanted to neutralize myself, I would touch the ground. And this plumbing works really well because this metal pipe, then the electrons can move through and the metal pipe goes down into the ground. And so I'm essentially touching the ground. So if there were any extra electrons on me, they would flow off of me. And so I'd call this grounding, and it's a good way to keep things neutral or make them neutral once you touch it. Now I'm away from it, I can get charged again. And they can't flow to the ground because I'm wearing tennis shoes that have a rubber sole. And so the electrons flow really well off of me. They also flow really well in metal pipes, but they do not flow through what we're going to call an insulator here real soon. They don't flow through our rubber. Okay, so with that said, I have now neutralized that little tiny pit ball. I have now taken a piece of, is that blue? Yeah, piece of vinyl. And so this vinyl is negative. And when Franklin first did this, he brings it close and goes, nothing's going to happen. Oh, whoa. And it wasn't much, but I hope you could see it on video. Did you see it attract? Right? It pulled towards it. I'll try it again. Until it pulls towards it. Now watch this. This is fun to see too. What if I let it pull towards it and I actually let it touch the vinyl? Okay, so I bring it forward. I let it touch the vinyl. Maybe I'll bring it close again. Oh, wait, now do you see it repelling? What's the difference? Well, I probably should draw a picture for this, because it took the early scientists, Franklin, really a while to figure this out. And here's what he concluded. At first, when you bring the negative near the neutral, and that's the key, neutral, it is not zero charge. It is equal, positive, and negative. And then he realized that the electrons can move around the surface of this little metal pith ball. And so this negative here would chase the negatives to what I'll call the far side of the pith ball. Since they left the front side of the pith ball, the front edge would be positive. So notice I am saying here that the object itself, the pith ball, is still neutral, but they have separated in charges. And if you mentally think about it as two halves, this half would be attracted and this half would be repelled, right? Because if this is negative, the like charges repel and the unlike attract. And so his thinking was, wait a minute, I have both attraction and repulsion. Now, if they were equal in magnitude, you would say, oh, they cancel and no net effect. But he also then realizes that the positive side of this pith ball now is a little bit closer. And because it's a little bit closer to the negative vinyl strip, it's going to be more attractive. So you might say that there is a force here, 1, that's being attracted, and there's a force number 2 being repelled. But force number 1, because it's a little bit closer, not much, but a little bit, it's kind of like the tides we were talking about. There's a differential in force. And this is a little bit closer. And so the net effect is attraction. And so you're going to get a net attraction. Now, not much of attraction, because you have both an attraction and repulsion. And I think you saw that here in the demonstration. You saw it attract, not by much. But then it got more interesting once I actually touched it. Once I touched it, then this pith ball comes over and touches it. And because it actually touches, and all these negatives are here, some of these negatives want to go on to here. Now, I wouldn't say one object is much bigger than the other. This is not what I'd call a grounding. This is just a sharing of charges. So once I touched it, I would lose some of the negatives on this vinyl strip. So I will draw less negatives. But what that would mean here is for the pith ball, once we've transferred negatives on here, now I would say the pith ball is negative. It is no longer neutral. And even though I didn't rub the pith ball, like I was showing you earlier with the vinyl, making it negative by rubbing, I still made it negative. And so it repelled because of these like charges. And so that's why the second time I approached it, after I had touched it, you saw it repel. Now, it didn't transfer much charge, so you didn't see much of a repulsion, but you did see a difference between attracting, then after I touched it, repelling. And here's the good news. The good news in all of that is, and this was Franklin's brilliance, he goes, I can explain all that. I can explain all that with these 3 principles. That the charges just transfer, that unlike charges attract, and like charges repel. So I'll say it again, even though the object is neutral, it still attracts. In fact, watch this. Let's run this experiment again, or something like it again. But this time, let me bring a positive near the neutral pith ball. Okay, so if I draw a picture, it would look like this. Okay, so I'm going to take the acetate strip this time. Because as we said earlier, the acetate strip is the one that I tear the electrons off. And I will bring it near the neutral pith ball. So I'll come back over to here, and starting with making my pith ball neutral. So let me touch the pith ball. And those electrons, as I said, are touching something much bigger, me, so they wanted to get onto me. And then maybe I'll get rid of them, so I'll touch the earth, so I'll ground myself. And so the pith ball is now neutral. Let me take my piece of paper. Let's see, this is the blue one, so there's the vinyl. Let me take the clear one, so here's my acetate. And let me rub it again. And as we said earlier, but it's probably worth repeating, as I rub it, I am scraping electrons off of both the paper and the acetate, but the paper is more electronegative. So as they come back, more of the electrons, not all of them, not even close to even 1% of them, but some of them go over to the paper, leaving lacking electrons here. A small percentage, but that's still quite a few electrons, because there's a lot of electrons in here. As I said back in the structure of matter, there are more electrons in here, even more atoms in here, than there are all the grains of sand on all the beaches and deserts in the world, plus all the stars in of all the, hundreds of billions of stars that are in our Milky Way galaxy, and then the hundreds of billions of known galaxies. So you take hundreds of billions times hundreds of billions, that's a lot of stars out there. But still, there are more electrons in here. So we're not transferring that many electrons. We're only probably transferring, 100 billion. Which I know sounds like a big number, but it's really kind of a very, very small percentage. And so I rub this. And let's see what happens, because this is also very interesting. So remember, this is a positive this time. And so I bring the positive near the neutral. Now, it's not much, but did you see it attract? Watch, I'll try it again. Maybe I'll get a little more positive on here. And bring it close. Oh, and it's positive. And now that it touches, look what happens. It repels. And you can see why this confused the early scientists. They're so used to the opposite. They thought, okay, well, if a neutral was attracted to a negative, then certainly over here, the neutral should be repelled from the positive. And it doesn't. But, as I said, here's Franklin's genius. He goes, well, wait a minute, it's really kind of the same thing. Let's come back to this discussion again. See, the neutral one, what ended up happening is, and there's the key, neutral does not mean zero charge. Neutral means equal number of positives and negatives. So this time, well, the time I showed you earlier with the vinyl, the electrons move to the back side of the ball. Over here, Franklin's argument is, well, now the electrons are attracted, and so the electrons move to the front side of the ball. They're being pulled away, again, conservation of charge, from over on the back side, and so we still have a neutral pith ball. We haven't put a net charge on the pith ball. It doesn't have more positives or more negatives. It's still neutral. But what we've done is we've separated them. The fancy word is we like to say it is polarized. And so if you think about this ball cut in half, again, this part, the closer part, would be attracted because they are opposite of charges. And the backside of the ball would be repelled, again, because they are like charges. But because the front of the ball is a little bit closer than the back of the ball, there's going to be a slightly more attraction than repulsion. And then because of that, then a neutral object will be attracted to the positive. And so it's kind of an interesting phenomenon to see here that it doesn't matter whether you take a negative or a positive near a neutral, they are attracted. And then, of course, once you actually touch it, so once I actually touch And in this case, I didn't mean for it to actually touch, but it did. And I'm glad it did, because I would eventually wanted to touch it. Once it actually touches, then the pit ball will actually then transfer some of these negatives off of the pit ball onto here. By the way, did you notice I'm still talking about the negatives moving? Right? I never said the positives moved. The negatives actually came off of here. So that's why I'm going to label this vinyl strip now as being still positive, but less positive. See, I only have 4 plus signs here, and here I had 1, 2, 3, 4, 5, 6. And so some of these come off. No, not that many, so this is still positive. But by taking the electrons off of here, I would now say the pit ball is positive. And this is after the touch. And of course, after the touch, if we have a positive pit ball and a positive acetate strip, those are like charges, and they're going to repel. And so that's why you saw them repel after they touched. There was actually a movement or a transfer of charge because of that touching. And so that's this whole fundamental principle. So I'll say it again. Notice I'm explaining all of this with this very simple property about like charges repelling and unlike charges attracting and conservation of charge. In fact, these neutral ones are the ones I always find the most interesting, because you don't mean to, but when you have a fan in particular, whether it's a ceiling fan or a desk fan or a cooling fan on your computer, that fan is spinning around. The whole point is that the blades of the fan move through the air, push the air. Let's say you're using a ceiling fan to cool yourself. The fan's spinning around. But see, those fan blades are designed to rub and push the air down. But see, that rubbing's actually going to make them charge. That wasn't the intent, but they will get charged. Especially in today's world, because today we like to make a lot of our materials out of plastic or vinyl. And so you've got a fan blade, and on my ceiling fan, it's got these 5 little arms coming off of it, and it spins around. And in my mind, every time I look up at it, I go, it's just rubbing against the air. It's building up a negative charge. So what's going to happen to any neutral object around? Now, the neutral objects are these little pieces of dust floating through the air. Most of the dust in a house are usually dead skin cells off the humans, and I'm in a household of 5. There's my wife and I and my 3 boys, and so there's a lot of dust in our house. And so it seems like every time I wipe something down to get the dust off, there's just more dust. And of course, it's kind of windy where we live, and we open the windows. We don't have any air conditioning, so the wind's blowing, and so we get a lot of just dirt dust. There's just a lot of dust. And I always look up at that fan, and I go, you know what? And so then I'll get on a little step louder, and I'll get to the top of that fan, and it is just caked with dust. And I know why. It is right here. It is it's vinyl, so I should go over here. But as the vinyl is spinning around, it gets negative charge, and then this dust attracts to it. Now, under the blade, you don't really see that, because the dust, if it tries to get under the blade, it gets pushed away. But on the top, it just sticks like crazy. And so if you don't get up there and clean it once a year, it's just a mess. I have a little desk fan, the same thing. It gets hot where I'm working, so I'll turn on the little desk fan, and it spins. Right now we have June gloom, so I don't usually turn it on. But if I look at that fan, the edges of the fan where it does the most rubbing, just caked with dust. My computer, the same thing. That little cooling fan just is loaded with dust. So I don't like that. But you know what I do like? Is I've got this other, I think it's a great invention. I got it at Home Depot. Now, it doesn't work this time of year because I don't have air conditioning, but it's for the heater. And all heaters have a filter. Most of them use a paper filter. That is, you put it underneath the filter, and so as the fan turns, it sucks air in from the house. It's supposed to go through the furnace and warm up and then come out and warm your house. That's how the furnace works. And so in mine, the air intake is in the hallway. It's down low. It's where all the dander from the dogs are, and it sucks it up. And if, I used to just have a paper filter, and then that dog hair and dander would all get caught. And so after a month, I would have to take that out and look at it and go, ooh, wow, that is dirty. Throw it away, put a new one in. Because again, I'm blocking the airflow, and so the heater doesn't work right, and so I put a new filter in. But then I came across this one at Home Depot that I just love. You put it in there, and it's made out of different materials. It's got about 5 different materials. And as the air blows through, it charges up the material. I'm not sure what the material is. It looks like it's a little combination of a metal alloy and some plastic. But I know that it builds up a charge, because then as the dog hair and the dander, it just sticks to it. And so it cleans the air much better than the paper filter. I put the paper filter in, and like I said, it blocks a lot of it, but still, the dander and the dust come out. But this really grabs it. So much so that within 2 weeks, not a month, within 2 weeks, I better take it off, because it is just caked with stuff. Like I said, there's 5 of us and 2 dogs. So there's just a mess under there. And what I really like is, because it's made out of metal alloys and plastic, you just hose it off. So you take it out to the front yard, you turn on the hose, you rinse it off, and you just see all this dirt and grime and dog hair and dander come falling off. You shake it out, make sure it's good and dry. When you put it back in there, when the furnace turns back on, it just gets recharged, and it cleans up the air. And so I really enjoyed that. Been using it for about 5 years. And so I'm not buying paper filters over and over again. It was a little pricey at first, but it was well worth it. And like I said, really cleans the air. But I thought that was really clever. In fact, my wife even has in our bedroom an ion, one of these air ionizers, and that's the idea of the air ionizer. It uses the air, it ionizes the air through a high voltage. This one you've got to plug in, but once it ionizes the air, the dust and the dander that come in just stick to that metal grade. So she's the same way. About once every 2 weeks or once every month, she's got to kind of unscrew, and the metal thing comes out, and it's just caked with dust. And so you got to wipe it off, dry it off, and put it back in. And so it uses this whole idea. In fact, this is most of the pollution control. Factories now just have these giant smokestacks now that as it comes out, they hit metal grid after metal grid after metal grid. And each metal grid is electrically charged. It grabs all the neutral little soot particles. And so hopefully at the top of the smokestack, no little tiny polluting particles and these little micro pieces are coming out. They've all been captured by these electrical grids. Well, maybe I said too much on that one, but I feel like I must give one more, because another one of my favorite is just the laser printer or the photocopy machine, because it works exactly like this. Have you ever noticed on a photocopier you do something like this? You take your original. You lift up the top, you put down the original, you close it, and then you see a light. Some of them just have a big flash of light, so it illuminates the whole thing. Others of them have a light that kind of scans across. But here's why that light is so important. If this right here is the top of the photocopy machine, so I put the photocopy machine right here, and I place it down here. As you're getting ready to hit the copy button, or maybe right after you hit the copy button, down here is either a drum or a rectangle. I'll just call it a drum. I'll do a rectangle. A rectangle of different, and it could be different material. I think ours here at the school uses a selenium block. But if you imagine then, okay, right here is my selenium block. I'll use this book to represent. Here's the selenium block. Here is the paper I want to photocopy. But as I put it on here, and the first thing I do to hit the punch button is the machine actually then rubs the selenium block, or vinyl. Vinyl's a little too, as you'll see, it doesn't work quite as well. But it builds up a negative charge on there. And the reason that's important is then this flash of light hits the paper, reflects off, and hits the top of the selenium. Now, the paper I'm trying to copy is white and black. The black parts absorb the light, the white parts reflect the light. So when I put it on here, the reflected light hits it. And when the light hits here, it kicks off those electrons. So here's what I'm trying to say. When I first rubbed it, the whole surface was covered with electrons. Now, after the flash of light, the only place there are electrons is where the light did not hit. Well, where the light did not hit was where there was writing, the black writing. So what I have on my selenium plate here is electrons in the same pattern as the writing of my original. Now we get to this whole discussion about what happens when you bring a neutral near a negative. And maybe I should show this picture again. So here's the negative, here's the neutral. And so the little machine, the photocopy machine, does this. It then sprinkles little fine grains of black plastic. You would call it toner. Puts the toner on here. Then it shakes them off. But they stick where the electrons are. You can't shake them off. Now, where there were no electrons, they fall off. So now what you have on this little rectangular plate is you have pieces of plastic, toner, in the same shape and the same pattern as your original writing. And so that's why this is a good example of electrostatics. It also explains why there's a big flash of light. There's another part, and the last part of this is then you take a clean piece of paper, a brand new piece of paper, and then you put that piece of clean paper on top of the selenium plate. And then one more thing, you press a hot plate and melt the plastic. See, because remember, the plastic is in the same pattern as the original writing. And so if you put the paper on here, and then you put a hot plate on top of it, it'll melt the little pieces of plastic underneath it. And they'll soak into the paper in the same pattern as the original writing. And now, the last thing is it just kicks it out. And that's why the last piece of it, when it comes out of the photocopy, if you fill it, it's warm. When it comes out, it's warm. So the flash of light and the warmth are all explained here in how this whole photocopying system works. Laser printer, by the way, really the same thing. Of course, you don't have an original to be copy, but what you do is you rub the selenium plate, or to make it smaller, you make a drum, so you run along the drum. And then basically you shoot a laser beam, that's why it's called a laser printer, everywhere you don't want there to be writing. And so you only have electrons in the location where you ultimately want to have writing. And then it's the same as the photocopy machine. You take a new piece of paper, you press it again, you heat it, the plastic melts, and it comes out of the laser printer, and it's warm. Don't confuse this, by the way, with the inkjet printer. The inkjet printer actually sprays jets of ink to make the pattern. And that won't come out warm. And so many home people, like myself, I have an inkjet printer at home. Those are the more affordable printers, although the ink costs quite a bit. The ones that work in a workplace, like here, we have all the laser printers. They cost a lot more up front. I think our laser printers are like $1,700. But they last much longer, they print much faster, and overall they cost a lot less. So that's why workplaces tend to have a lot of laser printers, and homes are often the inkjet printers. Well, I better keep going because this is our last lecture and we don't have really all that much time, but I hope I'm getting the fundamental idea across to you. In fact, I thought I would take a moment to then kind of show you a couple of fun experiments. You've seen me so far rubbing with my hands, but it's kind of nice to let something else do the rubbing, something that can rub harder than my hands and therefore build up more charge. And so this little machine, if I lift up the bottom, you will see this little electric motor here. Maybe I'll turn it towards you. But this is the electric motor. This is the wire that plugs in. When I turn it on, it's going to spin. This is the little belt. It's going to go around. It's going to rub right here. And it's going to transfer the charge up to the top. And so without me having to do the rubbing, I can just turn this on. And what will happen is this will build up a really large negative charge. And to kind of illustrate it, let me come over here. You might have been able to see that I also then have over here the other end of the rubbing where the charges are taken away is this little wire. And so this part's getting positive, but I've connected the wire to this little ball. So essentially we're taking the electrons off of this little ball and moving it here. So this ball becomes negative and this ball becomes positive. And so if I was doing something like this, these are actually being pulled towards each other. That's positive, that's negative. Now you can't quite tell that. Even if you were in class face to face, you couldn't tell that. But what I do want to show you is that if I turn off, and maybe actually I should leave just a little bit of backlight. I wonder if I put this down here and turned off both sets of lights here so I can still kind of see where I'm going. And I put the two close to each other. Hang on. My bad, I can't see what I'm doing here. Let me turn on a little bit of light. Okay. Kind of get this all ready. And when I turn it on, you'll actually be able to then get a visual effect. So now that I'm ready, I'll turn off all the lights. But you would call this lightning, if you will. This is a spark. And the electrons can build up so much on the negative that they actually push each other off the ball. And then, of course, want to go to the positive. And so that's essentially what a spark is, or what lightning is. Maybe some of you have done that with your feet. I know when I was a kid, that was kind of the fun thing to do to my younger brother. He didn't like it, but I guess that's what big brothers are for. I would go across and I would shuffle my feet. I would take off my shoes. I would shuffle my feet on the vinyl floor. It would build up a really big charge on me, and then I would go and shock him, and there would be this shock. And so that's what you're doing. You're using this electrostatic. You're building yourself up. And I don't know if you're positive or negative. Probably positive because we had a vinyl floor. And so vinyl, I know, loves electrons. So as I rubbed my feet, I was probably taking electrons off of me because the vinyl loves the electrons. And so I was probably positive, and then it was negative. Either way, I got a spark between me and my brother. And so like I said, I bad brothers like to do, and would chase him around the house till Mom would discipline me. And so that's this whole idea what you're seeing. In fact, it's kind of fun to watch this, because not only do you see it with shuffling your feet, but maybe you've seen this with what I'll just call lightning. I mean, in Santa Barbara here, we don't have too many electrical storms, but most of the country and most of the world have these huge electrical storms. So how do these clouds build up these massive charges? And the answer to that is they have rubbing going on. Now, the rubbing are these huge air masses, but there's still rubbing going on. Maybe it happens on your car. That's a very common one too. Your car, you've been driving down the freeway at 60 miles an hour. And as you're driving it down the road, there's rubbing going on. And so the charge builds up on the car. And oftentimes, because the tires are rubber, you don't feel it until you get out of the car. And then you get out of the car, you go to close the door, and it shocks you. Like, ow. Or the tumbling and the rumbling in the dryer. As it goes around, it rubs. That's why you have those static clean sheets. They'll work really well. Because if you don't put one of those in there, they come out with a lot of static charge on them. The clothes have been rubbing on each other. Like I said, this one's just fun to watch, because if I turn it on, the ball becomes negative, as well as all these little tiny pieces become negative. And of course, negatives repel each other, and they push each other off. Or maybe the wind that's blowing through your hair, and so this will kind of be the equivalent of hair, if you will. And as the wind blows through your hair, it's going to build up a charge. And each strand of hair basically does the same thing, and so they'll get the same response, usually a negative, and so the negatives repel each other. And so if all the pieces of hair are negative, they repel. Now remember, this ball is positive, so it should attract all the pieces of hair really nicely, and sure enough, we see that. And so there's our static charge. And then now you can see it kind of leak off here. And so they don't really want to be there. You got to keep the rubbing. And this, like I said, is so much charge, I have to keep the motor on for it to keep going, at least for most of it here. Well, that, as I said, is really kind of the fundamental basis of it. But let me show you a couple of other things here before we call it quits to this chapter. And one of them is the numbers. Because so far I've just been talking conceptually, and I haven't put any numbers in here, and I should. Starting with the units of charge. The units of charge are named after one of the great scientists working in the field, and so we call these coulombs. And so capital C for coulombs. If I take an electron and a proton, as we said earlier, they would have charge. And so let me give you a number. Now it turns out when Coulomb did his work, he did not have the technology that we have today. He did not take one electron and call that one Coulomb. There's no way he could do that. So he took a big group of them and called that one Coulomb. And it turns out that by the time he took that one group, and eventually, and it wasn't even Coulomb's itself, it was the famous Millikan oil drop experiment, who finally figured out what an individual charge was. But turns out one electron had a very, 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 very small amount of charge in terms of units of Coulomb. Now I suppose I better put a negative in front because the electron is negative. I think I said that earlier. So we say that the magnitude of the charge of the electron is 1.602 times 10 to the minus 19 coulombs. And then the magnitude of the charge on the proton then is a plus 1.602 times 10 to the minus 19 coulombs. Now, the important reason I give that number here is because what Coulomb's big claim to fame is he figured out that if you had one object of charge Q1 and another object of charge Q2, so let me pause right there. The symbol we will use for a charge is Q, the lowercase q, not the uppercase Q, what we did for heat, but the lowercase q. Sometimes we use an uppercase Q, but hopefully you won't confuse that with heat. And said if they are separated by a distance of r, then there is a force that can be calculated. And he kind of had the same guiding principles of Newton's universal law of gravity. Maybe you remember Newton's universal law of gravity. I hope so. It was way back in chapter 5, but hopefully you reviewed it this weekend getting ready for the final exam. But it said there was a gravitational force, and we had the masses involved, we had the distance involved, and we had this constant of nature. And we have the same thing with Coulomb's law. Coulomb's law says there is a force between these two. And the first part is it's the product of the charges. And so instead of the product of the masses, it is the product of the charges. It also depends on how far apart they are. In fact, I already used that argument when Franklin, who didn't have any numbers, he just did it conceptually. But as I said earlier, Franklin noticed that force number 1 would be a little bit more than force number 2 because it's a little closer. And so he noticed that the force changed with distance. It was Coulomb who put it in a mathematical equation. So that had to do with distance. And so he tried experiments, but like I said, he had a nice guiding principle. He goes, I wonder if this behaves a lot like Newton's universal law of gravity. Maybe there's a lot to be said here. Maybe the nature in terms of electrical forces follows the same kind of pattern as gravitational forces. So he tried a bunch of experiments and he was able to prove that yes, it does. Now there would be a constant, and so the constant we use for Coulomb's law is a K for a constant, not the capital G. And so this number would need to be measured, just like we talked about in the Cavendish experiment, where Cavendish finally measures the constant. Coulomb measures the constant and comes out to be 9 times 10 to the 9th. Now, the units would be a Newton and a meter squared over a Coulomb squared. And you kind of see that same pattern if you remember the G was the 6.67 times 10 to the negative 11 newtons, and then the meters squared. Of course, then down here we had kilograms squared because we were looking at the product of masses. Over here we have Coulomb squared because we're looking at the product of charges. And so I'll say it again, this would be the charge, this would be the distance between them, and then this would be that constant. So let me just do 2 quick calculations here. And I would say maybe the first one to do is, I'll keep it real simple. What if this distance between them is 10 centimeters? What if this is just 1 coulomb of positive charge, and this is then also positive, so they repel, but it's also 1 coulomb? I guess I would just say the force is, and so it would look something like this. And so I would put in the 9 times 10 to the 9th Newton meters squared over Coulomb squared. And then I'll put 1 coulomb for the first charge, 1 coulomb for the second charge. And the distance, and the reason I wanted to overemphasize this is, remember, the distance would need to be in centimeters. We had that same discussion when we did the universal law of gravitation. And so, and I forgot to square it here, square. And I made the numbers kind of easy on myself, although I do have my calculator here. But 1 times 1 is a 1, and then of course a 10th squared is a 100th. So this would be a 9 times 10, and this would be a 100th. Move it to the top, that's 100. And so times 10 to the 11 newtons, because the coulombs would cancel off and the meters would cancel off. And so that's how the numbers would work. Now, your author goes a step further and says, okay, this is the kind of the fundamental idea. But then he introduces you to a little deeper physics. It's called the electric field, whereas what I just calculated was the electric force. And he said, okay, let's try to study electrical forces a little deeper. And when you do that, you come up with something quite interesting. You see, the way I've said it so far is I made it sound like the only thing you need for 2 forces are 2 charges. And so this would say that if you had a positive and you had another positive, they should repel. But the early scientists, as they were doing some experiments, wrapped the second charge with a metal. And without getting in too much detail of the experiment, they noticed something quite surprising. And that surprising thing is there was no longer a force on that second object. It just disappeared. See, the reason that's important is, according to Coulomb's law Coulomb's law just says, look, if you have two charges separated by a distance, you will have a force. And that's what we have, other than we have a metal surrounding it. And this made them begin to realize that there must be something a little bit more going on. That is, somehow this first one is sending a message, if you will. It is sending over to the second one. And that sending over then is what you might call carrying the force over to the second one. In other words, it's not just that there's a force. There is a mechanism of how that force gets to the second charge. And this is that experiment that got them thinking about it. And they tried many other things as they tried to study, but the best way I can kind of illustrate it is maybe in a picture where I kind of say that, okay, something is coming over to the second one, but this metal blocks it. Whereas over here, this something is not blocked. And this something that is coming over, I don't really feel it. Excuse me, I don't really see it. It results in a force, and that's the force. That's the part I see. I do see the force. And so this is why I'm trying to say, this is like a step up. This is like a whole nother level. This is really saying that there is something else and something more going on. And that something more, that something else, they called an electric field. And so they did this. They said, and my blue pictures don't do a good job of illustrating what I really want to draw. So let me redraw over here. But they basically come to the conclusion that what happens is something a little more advanced than meets the human eye. And if you start then with a positive charge right here, so here is a positive charge, and just one by itself, of course you wouldn't have a force on a second one because you don't have a second one. But what they said is that first one makes, and I'll draw it a little better here in blue, something extending out, even if you don't have a second one. And so this something sticking out here, I'm trying to say, is an electric field. And so I like to say it this way, that the first one, the first charge, then makes a field. That field kind of goes out from the first one, and if it comes in contact with a second one, and so if there is a second one right here, then it's the field that then pushes on it. And that way, if you do some kind of experiment like this, where you block the field, you would have a second charge, but you wouldn't have a force because you are blocking the mechanism. The electric field then is that mechanism. And so here's the way we like to define the electric field. We like to then say that the electric field then has an outward appearance from a positive, but an inward appearance for the negative. Because again, if you let me redraw this, except I change this positive to a negative, and I put the second one right here, I think you will already know that there is a different result. In this scenario, this positive one gets pushed away, and in this scenario, the positive one gets attracted. And so it's too bad we can't see these electrical fields with our eyes, because if we could, it would be a lot easier to teach. But we don't. We don't see them. And because we don't see them, we have to draw them. And we try to draw them to help represent what's going on in nature. And this is how we've made our decision. We've decided to draw them with arrowheads going out from a positive and arrowheads going in for the negative. Another way of saying the same thing is, think about putting a positive near it. Which way would it move? So if I put a positive, sometimes we call this a test positive. If I put a test positive near it, it would be pulled in. So that's the way I will represent a field. I will draw it in blue, and I will draw it inward. Or over here, which way would the test particle go? It would go outward. So I will draw it outward. So all these blue drawings up here are supposed to be kind of what I'll call the advanced level, something that Coulomb didn't know. And it took scientists many years to figure out that it's not just a force. There is actually a field. There is something a little more complex about this. And that's what I mean by the electric field. So they needed a definition, and they said, well, here would be a good definition. Why don't we call the electric field E, I'll do it in blue, as how much force per charge. And so what we're saying here is if, and I'll come back to my picture, if you take away this second charge, and I'll take it away in both pictures, there still is an electric field. Oh, watch, you can see it if I continue on with the math. The force would be Coulomb's law, and so you'd have charge 1, charge 2 divided by r squared. And then this charge I'm dividing it by is charge number 2. That'll be my test charge. And so we have an equation that is almost like Coulomb's law. It just is lacking a Q in it. A second Q, I should say. And it only has the first charge. And that's exactly what I'm trying to say here. I'm trying to say that if this is Q number 1, Q number 1 will create a rounded field. Now, there won't be a force until you put a second charge, but the field is still there. The field is that mechanism. And when you put a second one, then there'll be a force. Unless, of course, you block it, like I said, which led to this discovery of that there's got to be something more going on. And so we like to give a little equation like this, which is, again, kind of like Coulomb's law, but it's just missing the second Q. And you can see now why it only has one Q in it. If I wanted to know the electric field, let's say right here, let's say 1 centimeter away, I would then plug it into that calculation. And notice, when I plug it into that calculation, the only charge I need is number 1. There is no number 2, right? Because we're not talking about the force. We're talking about how much field does the first one make. You don't have a force until you have a second one. And so that's why you would then multiply by the next Q to get the force. And so be careful with the homework problems. And that's why when I'm done with today's lecture, I'm going to say, hey, why don't I show you some of the answers on the homework one? And you can decide if you want to hang around and watch me do the answers or not. Because my hour and a half is coming close to the end, and so when I get to my hour and a half, I'm going to say, all right, we're done. And but I'm going to take another half hour to do a few more problems. And so you can decide if you want to hang around from that. But you'll see this discussion about the electric field, and that's the idea. In fact, let me just do a calculation for those of you who maybe don't have time to hang around. What if I went to calculate the electric field from a proton? If I were to say that this positive is actually then a proton, I guess I would come over here and do my calculation. And so the first thing I would put in is Coulomb's constant. So there's the 9 times 10 to the 9th, and then there's the Newton, then there's the square meter, and then there's the Coulomb squared. Then there's the charge of the proton. And if you remember a few moments ago, I said the charge of a proton was 1.602 times 10 to the minus 19 coulombs. And then the distance away, I said, let's calculate it at 1 centimeter away. So maybe, you know, we're thinking about putting a second charge right there. We haven't yet, so there's no force there yet. But if we did, it would make a force. And so if I put a distance of 1 centimeter, but let me put it in meters, so 0.01 meters. Then I can grab my calculator and get the answer. So the first number is 9 times 10 to the 9th. The next one is 1.602 times 10 to the negative 19. And the next one is 0.01 squared. And so I come out to be a number of 1.44 times 10 to the negative 5. And I'm hoping you kind of see the units back here in the definition. It would be a Newton per Coulomb. And sure enough, one of the coulombs cancel off, both of the meters cancel off, and you have newtons per Coulomb. And so that's how we would calculate the electric field. So again, the electric field is this. And I want to emphasize, it's a real phenomenon, but it's something we don't see with our human eyes. So what we do is we draw pictures, often in blue. You don't have to do blue, but that's kind of been the traditional normal and what I do. So I draw them in blue. But the real thing is you draw them with arrowheads in the direction that a positive would go if you put it there. You're not saying you're really putting one there. You're trying to emphasize that there is an electric field already there. There's just not a force there because you haven't put a second charge there yet. But you might. And so this is saying that if I put a second charge there, and if it was 1 Coulomb, this is how much force. Because this is saying how much force I would get for 1 Coulomb of charge. And I may put more or I may put less. And so it makes a nice calculation and a nice visual effect by drawing these lines. Well, one last thing, and I think I'm pretty close to that hour and a half, and that's good, because there's one last thing, but an important thing, that your author does here at the end. He says, remember way back in chapter 7 where we did conservation of energy? I'll go back all the way to gravity. Remember we did something like, I have a stapler, I don't have my mass here, but I hold it up, and because of the force of gravity, I said this has gravitational potential energy. That is, if I let it go, it would fall, it would lose gravitational potential energy, and it would gain kinetic energy. And we said the energy came from the force, and so you gave it this gravitational potential energy because maybe it started down here, and so you pick it up and you are pulling it away. In other words, the stapler and the earth are being attracted together, and so as you pull them, you're giving it energy, so now it has potential energy, and if you push it off, it releases that gravitational potential energy and it falls, and so as it loses gravitational, it gains kinetic. You remember all that? I hope so. Because your author doesn't take much time here, and I won't either, but he says the same thing is true for these electrical forces. It says this: if you had a positive and a negative, they would be attracted to each other, just like that stapler and the earth. And if you then pulled them apart, you have to do work. You have to apply a force. And as you're doing work and as you are pulling them apart, you're giving it energy. Now, we should then probably call this electrical instead of gravitational. But it still has to do with the position of them. So I'm still going to call it a potential energy. And I'm still going to put it in units of joules. But I would say then that this separation now, just like this stapler, this separation between the stapler and the earth gives it some gravitational potential energy. This separation between the positive and the negative gives it some potential energy. Electrical, because the force is electrical now, not gravitational. So it's electrical potential energy. And it would be a certain amount of joules. And what happens if you let them go and come together? Well, exactly the same thing as a stapler. If I let the stapler go, they come together. In other words, as they come together, they lose gravitational potential energy, gains kinetic energy, and the total energy doesn't change. Well, same thing here. If I were to let them go, this would come in and go faster, 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 faster. So it would lose electrical potential energy, and in the process gain kinetic energy. And so you can see why your author doesn't spend much time here. He just kind of wraps up the chapter. And that's what I'm going to do, is kind of just wrap up the chapter and say, look, this is just the same principle, except it's a new kind of energy. It is an electrical energy. And so we have to add that to our mix. Because remember, we had heat energy, we had gravitational potential energy, we had kinetic energy, we had translational kinetic energy and rotational kinetic energy. So those are the four energies we've been working with. And so we just have to add to this mix the electrical energy. Although there is one more thing, one last thing that's a little different. We like to take this electrical energy and divide it by the electrical charge. And so instead of saying how much energy it is, like say 10 joules, we would say, well, it's 10 joules per charge. We call this, and here's where it can really get confusing in the name. We call this potential, I guess technically electrical potential. So without energy. It would be measured in units of joules per Coulomb. And the clever person who did this is Voltaire. And so we call these volts. We give it a symbol of capital V. Why don't I just use your car battery as an example? When you go out and measure the voltage on your car battery, you're going to get 12 volts. What does that really mean? Well, it means this, that if I take this battery right here, so here's this car battery, and I say this is 12 volts, what I mean is one side is positive and one side is negative. And if 1 Coulomb of charge goes from the positive to a negative, that would give me 12 joules of energy. When I'm starting my car, something like 100 joules will move to here. 100 joules. Now remember, I get 12 joules for every Coulomb. So if I have 100 of them, that would be 12 times 100. And so the energy is 1200 joules. So don't confuse the voltage. And that's sometimes why we call it voltage, because the real name is electric potential. So don't confuse electric potential with electric potential energy. Electric potential is a way of labeling how much per charge. That's why you look at these batteries and you go, oh, it's only 12 volts. That's not much. Yeah, that's not much voltage, but it's a huge amount of energy because there's thousands and thousands, tens of thousands of coulombs in here. And so the total energy in here is a lot. It's only 12 joules per Coulomb, but there's a lot of coulombs. Well, that's the last thing of this chapter, and I'll call it quits, and I will let you decide then, because our hour and a half has been passed a little bit, and that's about as far as we can really go this semester, and we'll talk more about this than in Physics 122. But I just want to let the tape keep going, and so those of you who are interested, let's just go ahead and let me look at, I think I said there were 8 good problems at the end here that I think will help clarify all these ideas. And so you can decide to do the homework either on your own or keep watching here. I'm not going to do all of them. You have a reasonable amount, but 1, 2, 3, 4, 5, 6, 7, 8. Let me try number 51 first. And so number 51 here. And like I said, I thought I would just do this, partly because it's the end and you're not going to get a chance to ask me too many questions. You can tonight. I will keep checking my email and see what you guys might have. But I thought it would be helpful to do, like I said, 8 of these just right up front. And the first 3 are from the conceptual, and then the next 5 are from the calculation. So I'll get my calculator ready. But this first one, 51, is conceptual. And it says here, an electron and proton are released in a region of space where the electric field is vertically upward. All right. I picked this one because, again, I think one of the harder things is this electric field. And like I said, I like to draw it in blue, but they definitely say it's upward. And so let me draw it in blue. Let me draw it upward. And it says there is both an electron and a proton. So I'll put the electron here and the proton here. So an electron and a proton are released in a region of space where the electric field is upward. How do the electrical forces on the electron and proton compare? Okay, well, you can see it here in the mathematics that the force would then be the charge times the electric field. Now, this is conceptual, so they're not asking for any direct calculations, but when you look at this, you will see that both objects, the electron and the proton, are in the same field. They don't say what it is. Maybe I'll just make something up, like 100 newtons per Coulomb. That number is the same. Do the charges of the two have the same value? Yes, but opposite. So because they have the same magnitude, here would be my answer. My answer would be the force, the magnitude of the force is the same on both of them, but they're opposite in direction. And so maybe if I use a red marker to represent the force, the proton would be pushed up. Because remember, the way we draw an electric field is in the direction that a positive would move, which means then a negative would go the other way. They don't really say how this electric field is being created, but it could have been that down here was just a metal plate that had been charged positive. And remember we said we draw electric fields away from the positive. And if that was the case, then you can kind of see that this positive would be repelled from that positive and be shooting up. And then of course this negative would be attracted down to the positive plate and go down. But we don't even need to think about the plate because it's the field that really does the main push and the pull. And so that's what this one is all about. Now, 52 fits right in with this one. It's still conceptual, so I'm not going to do any calculation, but 52 says, how do the accelerations of the electron and the proton in question number 51 compare? See, the first part of it, 51, I'll come back. 51 says, how do the forces compare? And my answer was, the forces are equal but opposite. But when I go to calculate the acceleration, we got to go way back to chapter 3 on this one. The acceleration is force divided by mass. And I'll say it again, we already concluded that the forces were equal, but the masses are not. I told you earlier that an electron has a mass of 9.11 times 10 to the negative 31 kilograms. What I didn't tell you, and what you would need to do to finish this problem, is to look in the front cover or Google it. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. So the proton is about 2,000 times heavier. I think it's closer to 1,836. And a side silly note, I only remember that because when I bought my wife's engagement ring, and I'm old, so this was a long time ago, but I was a graduate student. I spent $1,836 on it, and when the guy rang it up, I go, "Oh, that is such a cool number." And he looked at me like I was crazy, and so I explained what it was. I said, this is the mass of the proton to the electron. I go, I think, and I'll go back and I'll try it. And so it's pretty close to that. And so when I proposed, and after I proposed, I mentioned that to my wife, and she says, "Don't ever say that again. That's not very romantic." So there's science, and I guess there's romance, and don't mix the two together. I had the same dilemma before we were married. We were sitting out at the beach watching the waves come in, and she looked at me and said, "Isn't this a great time?" I said, "Yeah, you know how much energy is in those waves every time they come in?" So, kind of ruins the moment. So, don't do that. But that's the scientist in me. And so, I just want to point out that the proton has, usually we just kind of round it to 2,000. We like to say that the proton is 2,000 times more massive than the electron. Okay, so that would tell me that they don't have the same acceleration. They do have the same force, but opposite. They do not have the same accelerations. In fact, the electron would have an acceleration about 2,000 times more. So this would accelerate down 2,000 times faster than this would accelerate upward. And so that's a neat one, tying together what we learned with Newton's second law together with this electric field and electric forces that fit in with this chapter. All right, well, if you're still hanging with me, let me take a couple more minutes. Let's do one more conceptual one, and it has a triangle. A lot of these have a triangle on them. Let's try number 58. And number 58 conceptually says this. It says an electron is observed to move with a speed of v naught at the point A. So they don't really say what the speed is. And so I'll just make a little dot. This will be point A. Maybe I'll put an E with a minus for the electron. Maybe I'll put an arrowhead to say, okay, that little electron is moving to the right with some speed v naught. And really no numbers. That should be. This is a conceptual one. At point A in space, where the electric potential is 750 volts. Oh, now they do give a number here. So maybe I'm wrong here. Maybe I do need a number. But I'm going to put 750 and with a capital V for volts. 750 volts. It moves to point B, where the electric potential is now only 550 volts. Okay, so maybe it moves over to here. Maybe I should put a dot. I'll call this point B. This is 550 volts. And so in other words, there's a decrease in the potential. Is its speed at point B greater than, equal to, or less than v naught? Explain. Well, you'll see why there's a little triangle here. This is not an easy one. But it gives me a chance to mention over here about electrical energy and electric potential. So this is, like I said, electric potential is not really the energy, but it's the energy per charge. So when it moves from 750 to 550, That's a change of 200 volts. That is a change of 200 joules per Coulomb. Now, I don't have a full Coulomb. So I guess if I really wanted to know the energy, and I don't think I do for this problem, I would take it and multiply by this change in potential, so this 200 joules per Coulomb. And then I would multiply it by the charge of the electron. But I wanted to put out the equation only to show you, let's be careful here. Because right now, I have done it all what I would call absolute values. So my point first here is, there would be a change of energy. Now, the energy would not be 200 volts because the electron does not have a full Coulomb. And you can see if you multiply this out, you would have a relatively small amount of energy change. But the point is, there is a change in energy. And so just like this stapler that falls, as it falls down and it changes its energy, then there is a corresponding, in this case, decrease in potential energy, so an increase in kinetic energy because of conservation of energy. So my first thing is to say, because there is a change in energy, there is going to be a change in speed. Because I know the total energy doesn't change. And so I have a change in electrical potential energy. Therefore, I also have a corresponding change in kinetic energy. So when this question says here, does it speed greater than, equal to, or less than, I can rule out equal. It is definitely not equal. Because if it had the same speed, so it has the same kinetic energy, and it had a change in its electrical energy, we would not have conservation of energy. So I'm going to rule that one out right away. Equal is not true at all. The bigger question, though, is this an increase or a decrease? And here's where I'd have to watch my signs here. I put there was a decrease of 200. Mathematically, I should put, hey, it is a decrease, right? And so I would put a negative. But also mathematically, I really should put a negative there. But again, since I'm putting a negative in both of them, I would say then this electron is going from here to a place of higher energy. This would be the equivalent of taking this stapler and say it's already moving, and now it goes up to higher energy. What happens when it gets more gravitational potential energy? It must have less kinetic energy. So this electron, as it goes from A to B, has an increase in electrical energy, and therefore must have a decrease in kinetic energy, because the total energy has to stay the same. So it must be going slower. And so that would be the answer here. It goes slower. Well, those are the conceptual ones. Let me try number 12 here. And number 12 in the exercises, if you're still kind of hanging with me for a little bit longer, and I know you got, a lot to do to get ready for the final, you can kind of decide how much to watch on here. But it says here a negative 20 microcoulomb charge experience a force of 25 newtons directed to the west. What is the electric field? That is its magnitude and its direction at that location. All right, well, this comes back to the calculation that I was saying. That if you take the force, and so what did they say? The force was 25 newtons. And at first here, let me just ignore the negative sign. Let me just calculate a number. But they say it is a negative 20 microcoulombs. So I'll put 20. I won't mess with the negative. Micro, if you remember, means 10 to the minus 3 coulombs. And so if I grab my calculator here. Oh, I'm sorry. I said micro, but I meant milli. Let me just double check. Thank you, Ron. Yeah, it's milli. It's milli, and so it's 10 to the minus 3. So I said it wrong. I wrote it right, but I said it wrong. It's milli. Okay, so milli. So this is 25 divided by 20 times 10 to the minus 3. And so this comes out to be 1,250 newtons per Coulomb. At least that's the magnitude, right? Notice maybe I should have put a magnitude symbol here. So I've only calculated the magnitude. Now if we go on to say and read here that it experiences this force directed to the west. Okay, so if I made a grid, maybe I'll start with a compass rose. And so compass rose is never eat soggy waffles. And so I have a negative charge, and if it's being pushed to the west, let me come back to the blue. Blue being the electric field. The electric field, remember, is what we indicate for where a positive would go. And so like we did way back here on 51, we draw the field in the direction a positive would go, and we of course have a negative one. So our field is opposite of our force. So maybe in the blue I will put an E, and in the black, I will put an F. So the force is to the west, if I read this right. Let me just read it again. A negative 20 millicoulomb charge experiences a 25 Newton directed to the west. What is the electric field, both its magnitude and its direction? So here's its magnitude, and its direction is to the east. Now there's more to this problem. It says if the charge is removed and not replaced, what is the electric field at that location? And the answer is still the same, right? This electric field, they're not really saying how it was created. Maybe it was created over here with this giant positive object. See, and we draw the electric field away from it. But if you take away the negative, the whole point of our discussion about electric field is this one is still here. The field is still here. You don't have a force because you don't have a second object there. But you still have the field. The field is created from the first object. The field is the mechanism of how it puts the force on the second one. So if you just have that original big positive one over here, you will still have that field. And that's what they're trying to get at in that one. Okay, well, I'll keep going here because, like I said, I wanted to do a number of them for you. And the number 12 was a good one. So it looks like we're about halfway through. Let me try number 16. And so number 16 says, what is the electric field 5.3 times 10 to the minus 11 meters from a proton? All right. So if I put a proton, I would say, since the proton is positive, it would make a field that would look something like this. And so there's the field. They're asking me to calculate the field some distance away, so I'll just kind of make a little dot right here. And they say this is 5.3 times 10 to the negative 11 meters. What is the field at that location? Okay. Notice they did not say there was a positive or a negative charge there. And again, that's exactly why. We don't need it. The proton itself makes the field. So then if I put in that equation, if you remember we worked it out, we started with F over Q and said that would reduce to just having charge 1 over R squared. So I would put in the 9 times 10 to the 9th newtons meters squared over coulombs squared. Since they said it was a proton, I'd put in the 1.602 times 10 to the negative 19 coulombs. I would put in a distance of 5.3 times 10 to the negative 11 meters and square it. And by the way, if you're wondering why they picked that number. That is actually the distance that the electron is away from the proton in the hydrogen atom. So this is really saying what would the electric field be where the electron is as it orbits around in a hydrogen atom. And so if I grab my calculator here, it's 9 times 10 to the 9th times 1.602 times 10 to the negative 19. Then divided by 5.3 times 10 to the negative 11 squared. And that comes out to be, because the denominator is so small, a big number of 5.13 times 10 to the 11th. And again, if you look at your units, you'll see the meters squared cancels off, and only one of the coulombs, so you'll be left with newtons per coulomb for the electric field. And it would be pointing away. I don't know if that's important here, because it says what is the electric field from the proton, but it would be away. Here's another fun one, 17, a little more advanced. Maybe I better give myself a little more room to do 17, so I'll move down here. And so number 17 says what? It says, what is the electric field midway between a 2 Coulomb and a 6 Coulomb that are separated by 2 meters? All right, so right here, and I'll put a little plus because they say it's 2 coulombs. And then over here, 2 meters away, there is another plus of 6 coulombs. I think that's what I read. Yeah, 2 and a 6 separated by 2 meters. Now, midway between would be right here. And the reason I wanted to show you this one is this one actually then has 2 fields that we would just add together. We did the same thing with net forces. Remember, this compares to gravity a lot. So net force, we would just add the 2 together. And so this is really what they're after. They're after, he didn't use the word net, but it's the net electric field. And so if I was drawing a picture, I would say this positive would make a field to the right, and this positive would make a field to the left. Now, this one is a little bigger in charge, so it would make a bigger field. So maybe I will draw them this way. And so if I wanted to get what you might call the net field, and we called this field number 1, and we called this field number 2, like we did back in chapter 3, this would be like one person pushing to the right and another person pushing to the left. And so to get the overall total, you just add them together, like vectors though. And so when I say the word add, you don't literally add them. These are opposite in direction. And so it's been a few weeks since we spent emphasizing that word, that vectors have a magnitude and a direction. Their direction is just as important as their magnitude. And so a better word than add them is really combine them. And so remember we said they could be combined in the same direction, they could be combined in opposite directions, they can be combined at right angles. And so how they line up is just as important. So I'm going to combine them together, add them together, but it's really mathematically a subtraction. So let me find the strength of field number 1. This would be Coulomb's constant times the charge divided by the distance squared. So this is 9 times 10 to the 9th for the constant, then times 2 for the charge, and then the distance away is 1 meter. I guess I didn't put units there, but we've done this a few times, and I'm trying to shorten up the video a little bit here. So why don't I just put newtons per coulomb for the answer, and then you could even see when you multiply this out, you get 18 times 10 to the 9th. That's a pretty straightforward one. Now field number 2, I could even probably save a little time here by realizing everything would be the same except this would be a 6 instead of a 2. So it'd be 3 times bigger. And so it would be a 6 times a 9, which is 54. So 54 times 10 to the 9th newtons per coulomb. So if I go to finish this problem and say what is the net, I would have the 18 times 10 to the 9th minus the 54 times 10 to the 9th, which must make 36 with a negative, times 10 to the 9 newtons per coulomb. And so the net effect is 36 billion newtons per coulomb in the, well, in my picture anyways, to the left. They didn't really give me a picture, so depends on which side you put the bigger charge. All right, well, again, hopefully that wasn't too fast, but I do think I should probably shorten this up a little bit. You guys are going to see the video and go, oh, that's really long, and I don't want to scare anyone there. And so let's do two more here that I promised that I thought would be good. Number 21, I'll change back to black here, is a good one. But this 21 says, the electric potential energy of an object at point A is known to be 40. Okay, so I'll put a little dot, I'll put A, I'll put 40 joules. Let me check, did they say electric potential energy or did they say electric potential? They said energy. The electric potential energy of an object at point A is 40 joules. If it is released from rest at point A and it gains 50 joules of kinetic energy. Okay, so maybe it moves over to here. Maybe I will put over here this, how should I represent electrical energy? Maybe I will put electrical potential energy. You see, the kinetic energy, since they said it was released from rest, is 0. And they say it moves over to point B. And so as it moves over to point B, at this spot, it has 50 joules of kinetic energy. And so we get to the question then that says, what is the potential energy at point B? And this is that whole part I was saying, conservation of energy. Well, we have a total of 40. And so if you're going to gain kinetic energy, you must lose the same amount of potential energy. So this must have a negative 10 joules of potential energy, so that the total is still 40. And so the total energy didn't change. We lost electrical energy, we gained kinetic energy, just like the stapler going down. Although this is more like digging a hole and the stapler falls into the hole, because we've gone below 0 for our energy. We've gone negative, so we've gone, if the ground is 0, then we have to dig a hole so it'll fall down in there. Well, one more then, and then we'll call it a wrap for the semester, other than you still got the big test to do, the final exam on Wednesday at 11 o'clock. And of course, at this point, you haven't started the test, but you soon will. And so 23 here is, how much work does a 12-volt battery do by pushing 2 millicoulombs of charge through a circuit containing a light bulb? Well, this is a lot like one I was just talking. I didn't write it out, but there's the 12-volt car battery. This is again trying to say that to get the electrical potential energy, you would take your electric potential and then multiply it by the charge. Because again, this electric potential, this voltage, is not really the energy. 12 volts does not mean it has 12 joules of energy. What it means is it has 12 joules per coulomb. So this is 12 joules for each coulomb. And in this case, let me come back to the number. They say it is only 2 milli. So this is a small amount of charge, but 2 millicoulombs. So of course that cancels off. And so 2 times 12 is 24. So this would be 24 times 10 to the minus 3 joules, or just simply 24 millijoules. All right, well, it's been a great summer and a different summer. I hope you've been able to get a lot out of this, and really focus your attention, work hard on the final exam. I'll be sending you out some emails to get you ready. I'll be working on the grades. Probably will have the grades. I'm hoping by Thursday night. It might flow over into Friday. Depends how much time I can spend on it. But I'll have pretty much all day Wednesday to grade and all day Thursday to grade. And next fall, again, we're online, so I won't get a chance to meet any of you in person, but I'm hoping in spring. Because a lot of you are going to take 121 in the fall, and then in spring, we'll do 123 together. And so hopefully we'll all be face-to-face, 123, and I'm looking forward to that time together. But until then, bye now and study hard.